Okay. Nice to see you all today. So it's this is really the main course, the main topic of this course today. We are going to talk about localization. So that's really it's a really hot topic. Although started some time ago with Phil Anderson, we'll talk about that, and I will show you that this is still a very challenging effect, very challenging phenomenon to observe, especially in optics. So we'll talk about that. I will try to give you many examples. There will be very little calculation, so don't worry, today it will be fun. Okay, so let's start. By the way, I put on the Moodle, I put the schedule for the exam, for the presentations. Okay. Starting not next week, the week after. Okay. So if there is any question or any need, or if you want to ask question about your paper, don't hesitate to come to me. Don't wait the last minute anyway. Okay. So let me just briefly introduce the topic today. So we are going to talk about what is called mesoscopic effect. Mesoscopic physics. So you'll see that you remember that we discussed earlier different approaches to describe multiple scattering of waves of light, and we developed this approach here, which is a classical approach based on transport theory, diffusion, wave diffusion. Okay. Transport description turns out to be inadequate in certain cases. So that was last week. We started last week with the example of the speckle pattern. Okay, so when you look at light scattered by a medium, what you observe is this type of image here, which is a strongly, strongly varying picture with very strong light at certain point and very dark at other points. So fluctuations are huge, and that was the main message of last week, that we have in this system strong fluctuation that cannot be described by transport theory. Okay, so this is really something that you see every day when you play with lasers. Speckle pattern, we talk about the total transmission, which does not average. Also, we talk about the phase singularities last time. Okay, all these physics, which we described last time using statistical approaches, actually reveal a different nature of light. Light is not particle, but it's a wave. Okay, so it's a quantum phenomenon. And this is what I'm going to push forward today. Probably I will talk about extreme situations where this order is very strong. Maybe those effects are exotic, okay? But they are very important and they are very fundamental to the physics of waves in these systems. Okay? So, which phenomena can arise from the non-classical character of wave transport, from the quantum nature of waves of light. Speckle pattern, so this is one example. Strong intensity fluctuations cannot be predicted by diffusion theory. In multiple scattering media, some interference effects survive averaging over a statistical ensemble. Okay, if you average over many configurations, okay, that was a question here. Is this pattern going to self-average or not? You remember, is the speckle pattern a self-averaging quantity or not? This is one point, but we'll see here an effect that there is no doubt about it. Some interference effects can survive and will survive anyway to any average over configuration of the disorder. So we talked last time about non-Gaussian statistics, long-range correlation. Also, we mentioned that last time. We discussed that. And what I'm going to talk about today, the first effect, which is called weak localization, is about the coherent backscattering. And finally, we'll talk about strong localization, Anderson localization of waves. Okay, so what did I write here? So these effects affect the diffusive behavior of the dynamics of the diffusion. Okay, we see that the diffusion doesn't behave as expected. Okay, and this is really fundamental aspect of light, of the quantum nature of light. Okay, so this is my outline. I will talk first about the coherent backscattering, or in other words, the weak localization effect. That means that this is an effect that you can observe even if you are not in a strongly scattering medium. Okay, and then we'll move to Anderson localization of light. This here requires a very strong scattering of, scattering center, strong disorder to observe localization. And we'll introduce that, and we'll give you different signatures of localization. Okay, and I will show you different examples in 1D, 2D, 3D, because this is a phenomenon that depends on the dimension of the system, of the scattering medium. Okay, so you have some references here. I'm not going over them, but this is for you. I mean, if you want to get more information, there are some review papers. Okay, so let's start with coherent scattering. Oh, that's a reminder of something actually that's a slide from a previous course. I'm sure you remember this slide here and these guys. Remember? Mm-hmm. So what we discussed at that time was the distribution of the light which is reflected diffusely by a scattering medium. Okay, and you remember that we have this Lambertian distribution, the cosine law, P is P0 cosine theta. Okay, so if you consider simply the regime of diffusion, okay, like particle bumping on this scattering surface, what you see is a kind of not uniform, it's a cosine theta distribution with angle. Okay, if you still have specular light, some reflected light, you may see a spot like that, but in what you expect to have is something which is which has equal luminance in all directions. Okay, so that's the case of isotropic radiation. Okay, what I want to show here is that this picture actually is not true. If you look carefully here, you'll see something which is not following this law here. Okay, so let's see the experiment setup. The experiment setup is the following. So you have a laser coming onto the sample. The sample is here, so multiple scattering sample, this sphere, for instance. Okay, and you measure what is backscattered, what is coming back from the scattering medium. Okay, so part of the light, the light will come back. Okay, and it is reflected by this beam splitter on the CCD camera. The CCD has a matrix of pixels. Okay, so actually all these pixels measure different angle of the backscattered light. Okay, you could also scan with angle detector. Okay, this is a simple way to image directly the backscattered light from the system. Very important, you don't want to see the direct reflection, okay, the specular light. So to do that, you use polarizers and lambda over 4 plates just to select the cross polarization. Okay, so you come with one polarization and you measure the other polarization. Okay, so with that you are sure that you don't have specular reflection from the surface, which will be trivial. Okay, and so let's measure what we get here. Okay, for one realization of the disorder, what you expect to see is the following: a speckle pattern. Okay, that's for one realization, and then you average over realization. Let's say you have a liquid with particles. Everything is moving with some Brownian motion, for instance, or you rotate your sample. Okay, and you average over this picture. And what you see is not a uniform pattern. You don't see the cosine theta, but you see on top of the cosine theta, you see a peak here. So this is a little bit exaggerated. The peak is like that. Okay, so you have, in fact, you have the cosine theta function, which is here, which is the background. Okay, you see 1 is here, so that's the background. And on top of this background, you have a small peak on top of it. Okay, that is persistent and that survives the ensemble average over configuration. Okay. So one interference effect seems to survive configurational average. Okay, and let's try to understand where this comes from. Okay. So observation. So we have the classical diffuse light. Okay, which is the cosine theta function, and on top of that there is a what is called a cone, a current backscattering cone. Okay. So an enhancement of the backscattered light around the direction 0. So 0 means perfectly backscattered in the same direction as the incident direction. Okay. So a peak of intensity is observed in the backscattered direction. And the peak is twice as high as the incoherent scattering background. So if you have 1 here, you will have intensity 2 here. Okay. The angular dependence of the cone is directly related to the transport mean free path. So remember, transport mean free path characterizes the scattering of your medium. Okay. So the smaller the transport mean free path, the stronger is the scattering in the medium. So if you have a system which is more and more scattering, then this cone, this peak will get larger and larger. It's 1 over KL star. Okay. So if L decreases, the angle of the cone will increase. Okay. So you can imagine that for very weak scattering medium, you will have a peak like that, but so narrow that it will be extremely difficult to measure. Okay, so it will come completely unseen. But if you have sufficiently strong scattering, then you start to see something. And if you have good resolution in your measurement with angle, okay, you can actually catch this effect. It's not just Gaussian or something like that. It has a cusp shape. That means that it has how do you call that? It's like a peak here. Okay, so there is how do you call that? There is a singularity in the second derivative, if you want. Okay, so at small angles, the decrease from the peak maximum is linear. So you have like 2 lines at the top. Okay, so there is a very strange shape actually. Okay, that you observe. When was that discovered? The discovery was found independently in 2 different fields. So in the field of electrons, solid state physics, and in optics. So actually, those are very early works. 1966 here. So here you cannot measure the backscattered light, but they measure the conductivity, the conductance of their sample. Okay, and they show that the conductance actually behaves strangely when you go to lower and lower temperatures. Okay, so this is called breakdown of Ohm's law in thin metallic film at low temperatures, and this is due to the fact that we have dirty metals, metals with many defects. Okay, many scattering. And electrons can be seen as waves, okay? But at that time, they didn't really understand. They didn't have the interpretation for this effect. Came in optics the work of the Wolf here. It's a prediction, actually. So he predicted that there will be a sharp peak exactly at the backscattering direction when you average over intensity. And these effects should survive ensemble average over disorder. Okay, so that's a prediction in the field of turbulent atmosphere. Then when came the first measurement of the backscattering cone, I give here some those are really the first references on the topic. You can see here a very nice resolution of the cone, many points here, so they can catch really the peak, the cusp here. And you see for two different values of the transport mean free path for two different degrees of scattering, you have two different width of the cone, and you see the tip here is very well resolved, which was really a challenge at that time. And it's not the case here. You see. Okay, so where is this peak coming from? Any idea? Any suggestion? What could be the interference effect that survives any averaging? You can change the position of your scatters as much as you want. This interference will be always constructive. Any guess? Not for those who know who know already. So look at this picture here. So this cone, this coherent backscattering cone, arises actually from the interference of two reciprocal multiple scattered trajectories, okay, that visit the same scatterers but in opposite direction. Okay, so you have the blue path here that goes through these scatterers, and the red one will go through the same scatterers in the other direction. Okay. And you see that if A and B are exactly in the same direction, so if you look really in the backscattered, the backscattered direction, what you get actually is a constructive interference that have exactly the same path. Okay, and whatever you can change the position of the scatterer, you can have consider many different trajectories. The trajectory and its reverse.
The angle is like preserved.
Which angle?
Like when they are the same direction, and they're scattering all over the place,
yes.
And then like the angle, like
of the output.
Yes.
Yes. No, it's not. I mean, you
not
you
with
can scatter
the same angle, but
you can scatter in all angles, but there is one angle which is exactly the backscattered angle, for which you see we will calculate next the difference of phase between the two, okay? But when theta equals 0, then there is no phase difference, and you have a constructive interference here, okay? So what is important actually is the phase difference between two passes. And what is important also, what is very important, is what is called the time reversal symmetry. Are you familiar with this concept, time reversal symmetry? Time reversal symmetry or invariance means that by reversing the time, everything comes back to the same state. Okay, so going through one direction or going backward in the other direction, okay, you accumulate the same phase. Okay, so for every path, it is possible to find a time reversed path which has exactly the same. Which follow exactly the reverse order of scattering and has exactly the same phase accumulated along the path. Okay, so this is called time reversal invariance. How do you lose it? How do you lose the time reversal invariance? For instance, if the scatterer they move fast enough so that one beam and the other one, I mean one trajectory and the other, they don't see the same system. Okay. So in optics, that would mean very fast movement. That's not possible. But in acoustics, you may have this problem. So if the scatterer moves, or if you have the presence of a magnetic field, okay, the magnetic field breaks down the time reversal symmetry. Okay, so going in one, I mean, circling the B field in one direction or the other direction is not the same. Okay, and that's a way actually to destroy the current backscattering cone. Okay. Okay, so this is maybe a strong constraint. I just mentioned here that reciprocity is enough. You don't need to have full time reversal symmetry. I can explain that briefly. Reciprocity means that if with source A here I measure on B something, if I put the source on the other side and I measure on this side, I get the same measurement. That's reciprocity. It's not as strong as time reversal symmetry. time reversal symmetry is like that. I mean, changing time in minus time, okay? T in minus t, you go just backward, like taking a movie going backward, you go back to the initial points. Okay, so those are, if you want to learn more about that, I put some YouTube movies here. Okay, so let's go a little bit deeper in that story. That's really the only calculation that we'll do today. It's not very difficult. So let's say we have k incident here. So we have the incident vector here, ki. Okay, incident on the scattering. So we have a scattering medium here. Okay, and the light is getting out of the medium in the direction kf. Okay. So let's say that the first scatterer to scatter light is R1 and the last one is Rn. Okay. So what is the path difference between the two? So you go like that and like that. So what is the phase, the path difference and then the phase accumulated along this path? So you see that you have, if they are not at the same position here, they are not parallel to the input or perpendicular to the incident wave. So you have actually this d1 distance here plus this d2 distance here. Okay. So because of the sign, if you are careful, delta phi will be 2 pi over lambda. So k times d2 minus d1. Okay. d1. So this d1 here is ki, where is ki? So here, ki, so this is the dot product of ki times Rn minus R1, so this vector here, okay, so that's the dot product, so it's yes, this distance is actually this time, this, the projection, you take the projection of Rn minus R1 onto ki, okay. And d2, this distance here, is the projection of kf, this distance over kf, okay. So this is written with the dot product kf times Rn minus R1, okay. So there is a sign here. So if you put them together, you get 2 pi over lambda kf plus ki times Rn minus R1, okay. So how do you calculate kf plus ki? I just put you the calculation here. If we have ki equal kf equal k, okay, it's the same light, okay, so it's the same amplitude for the k vector. Theta is the deviation between the incident and backscattered directions. So you can write, here, so you can write kf plus ki square, okay. Here you just, so this sum actually, so it's the sum of the kf and ki vector here. You use the cosine identity or formula, okay. So it's k square plus k square minus 2k square cosine theta. You factorize 2k square times 1 minus cos theta, so it's 4 times sine square theta over 2. Okay, you take the square root of this square here, replace here, and you get so 2 sine theta over 2 here times 2 pi over lambda times, so this distance Rn minus R1, we call that R, this distance here, times cosine alpha, this alpha here. Okay. Let's consider a medium with many scatterers, so a dense scattering medium. Okay, so more or less there will be you won't have big difference between the position of Rn and R1. So we can neglect alpha. We can take alpha equals 0 to simplify. So the cosine alpha disappears. Okay, and the small.
Can you say again what is big R?
What is what?
The big R?
R is the distance between the two, so actually the projection.
The red one?
Yeah, no, so the right one is, let's see, R. So no, this is R, and this is R cosine alpha, okay?
Okay.
So this is R. This R, the smallest R that you can have is what? The smallest distance between two scatterers, okay, is given by the transport mean free path, okay? If you remember the picture of the random walk, each step of the random walk is a jump of L star, one transport mean free path. So the smallest distance between two scattering events is L star, okay, the transport mean free path. That's the smallest value of R. Okay, so if I replace this value here, I get the following. Delta, so it's not replaced yet, so delta phi is 2 pi over lambda theta R, or theta L star for the minimum of R. Okay, so if you have two inverse trajectories inside the scattering medium, they accumulate a phase delta phi here, which is 2 pi over lambda theta R. Okay, to have a constructive interference, we want to minimize this delta phi. Okay, so let's say that delta phi is around 1. Okay, and this defines a critical angle. Theta
Why not 0?
Yeah, 0. Okay, 0 gives you a the maximum interference. Okay, 1. But I want
There
to
is
know.
no phase.
Right, that's when they are perfectly in phase. Okay, but you have some degree of freedom. Okay, with the angle theta that allows you to consider that you still have interference. Okay, less constructive, but you still have interference.
So we said
I want to get actually the angle of the cone. What is the angle of the cone from this expression? Okay, so you can define a critical angle theta c here, which is 1 over kr. Okay, and the smallest value of r being L star, you obtain the formula that the angle of the cone is theta c 1 over k L star. Okay, so that gives you the width of the cone, so the largest width of the cone. Actually, R can be larger than L star, so this cone, this angle is getting smaller and smaller as you have longer and longer distance between the scatterers. Theta c decreases with longer path. Okay, so if you have the smallest distance between two scatterers, okay, is L star, you get theta c. If you have a longer distance, okay, then you get a smaller value of theta here. So theta c decreases with longer path. That means that the tip of the cone will be affected by any effect on the long passes. The longer the passes, the narrower the tip of the cone. Okay, I show you how it comes here. So first the factor 2. The factor 2 is easy to understand. Okay, if you have the interference between A and B, so you have A plus B squared. Okay, you develop the square here, and you get A. You can factorize if A and B are equal. You can factorize by A squared times 1 plus. So exponential of the phase difference here. Okay, and this gives you actually a cosine term. So it's twice 1 plus cosine the phase difference here, and you see that if you are exactly at the backscatter direction, ki is minus kf. If you go back in the same direction, then you get actually 0 here, so 1 for the cosine. So 1 plus 1 equal 2. Okay, so you double the background. So this is the incoherent scattering. That's the 1 of the cosine theta background. Okay, and this is the interference term that gives you plus 1, an additional term that gives you a cone which has an intensity of 2. Okay, if kf is equal to minus ki. So you get an enhancement of the backscattering by a factor 2. So this is in the case where you are exactly in the right direction. So that's what you observe. So you see, you can see the background is really the cosine theta, and on top of it you have this build-up of the cone. let's see it from a different perspective, from the perspective of the random walk, and you'll understand better how the tip of the cone is built up. So you remember the drunk guy here. So is changing direction and making step of L star, one transforming free pass in random directions. Okay. And if you remember, we said that is going to explore larger and larger region in a diffusive way, okay, following actually this equation here. So the square, the variance of the extension, the region explored by the drunk guy, it goes like 6d times dt. Okay, so it goes, so the square goes like time, meaning that the square root of, so r is going like the square root of time, okay? That's diffusion. Okay, and d is the diffusion coefficient, which is CL star over 3 in 3 dimensions. Okay, so that's typically how over time the region explored by the drunk guy increases, okay? Although it comes back to the center in 1 and 2D, he explores larger and larger regions. Okay, so if you replace that here, okay, you get that delta phi is 2 pi over lambda theta. You replace r by this expression, by the square root of this expression here. Okay, c times t is the length of the path followed by the guy, the drunk guy. Okay, so what you find is that theta c is lambda over square root of 2 L star s. Okay, so that tells you that the longer the path inside the scattering medium, the longer the path, the narrower will be the angle. So that describes the tip with the tip of the cone.
And what is phi?
Here,
Yes.
that's the phase difference. That's the phase
The
difference
phase,
between A and
okay.
B, right? I'm using the same.
And they have
same,
an equal phase, A and B, right?
They have.
An equal phase.
They have a phase difference of delta phi if you don't have the same angle. At the same angle,
הפרש פאזה שם, זה ביטוי להפרש פאזה. בין A ל-B.
there's a phase difference.
Okay.
Okay.
חשבתי שהם כאילו שהם מקבילים.
Okay, I don't go into details here. Okay. If you want another way to look at it, very simple way, you can think about these two scatterers as the double slit experiment. Yes, you know this experiment. You have two small holes, okay, and you have photons coming there. What you observe on the screen is an interference pattern, okay. This is because you have actually the sum of many sine waves like that, okay, and they are only in phase here at the center here. So you get a peak, and then there is a dephasing between them that actually builds the edge of the cone here. So you see that the longer passes, which correspond to fast oscillation here, you see double scattering. So if you look at different degree of scattering, double scattering will build this cone here. Three scattering will build this cone. 5 will build this cone. 10. An infinite number of scattering. Okay?
It's the order of what? Like the degree
So
of what?
think about the trajectory of the light inside the medium, okay? So it's going to be scattered many times inside, okay? So the deeper it goes inside the system, the more scattering there will be, okay?
So the number of the order is the number of times
of scattering event. Yes, of scattering event.
Okay.
So imagine that
Yeah.
so imagine that the longer the trajectory inside the system,
Okay.
the more sensitive it will be to a small phase difference.
So the longer scatter. Okay, it's what you said before.
Yeah.
Okay.
Just another way to look at it.
The relation between L and theta.
Right. Exactly right.
Yes. Okay.
Okay. So anyway, we end up with this result, which is the main angle of the angle dependence of the cone. Okay. So if you understand the role of longer and longer trajectories, you understand that if you take a sample which is a slab which is cut somewhere, okay, you are going to cut long trajectories inside the system. Okay, so this is called finite size effect. The current contribution is reduced to smaller angle for longer passes. So all effects which affect long pass will round up the cone. Okay, so for instance, if you have absorption in the system, so the longer passes will be absorbed, so you are going to miss the tip of the cone here. Okay, so that is going to round up the cone like that. Okay, this is just, you know, more details in this story. You can see here the role of absorption or gain. In that case, that's gain, so the inverse of absorption. Interesting here, you can compare different materials. So you probably know Teflon, okay? So it's a white kind of plastic, very hard plastic. Shock, okay? Those are samples of particles, dielectric particles, and you see for these different things. So you can see that the Teflon actually has a very, very narrow cone, so it's undetectable. Okay, and then when you go up, you get larger and larger. But this is a very, very small, so see in degrees here. We're talking about very small angles for the tip at least. Okay. So there have been many experiments around this principle, around this concept of the backscattering cone. I show you a few of them. You see, it's very interesting. I mean, it goes in all directions. So this is one example, for instance, of a scattering medium made with these kind of needles here. Did I write what is it exactly? Nanowire materials, okay. And they can change actually the length of the wires here, okay, and they find different backscattering cones with different width, okay, and from that you can measure the transport mean free path. So here they plotted the transport mean free path LT as a function of the wire diameter, not length. So the wire diameter. So you see how the mean free path decreases. The system becomes more and more scattering. And this is the optical thickness, which is the length of the sample divided by LT, transport mean free path. So that's an interesting way to do what they call spectroscopy of this type of this GAD, so gallium phosphide sample. So what they call spectroscopy means actually measuring the mean free path of the system. So that's in optics. In a very different field, the field of cold atoms. Some people are working with cold lead, no? So you know that using lasers you can cool down atoms. You can make them almost immobile. Okay. So the temperature can go down to nanokelvin. And this way, actually, when you cool down the matter, the atoms, the quantum nature of these particles comes to the surface, okay? And it seems here, actually, they can show this coherent effect of the backscattering enhancement of the light in an experiment. So the experiment is very, very complex. You can see the setup here. But yes, they can show actually. So these matter waves, okay, it's not light. It's matter wave scattered by a speckle of light. So it's just the opposite. Instead of light scattered by matter, here they use matter, so atoms, atomic waves, if you want, scattered by a speckle, an optical speckle of light. Okay. So that's the disorder system. Is the light, is the speckled light. That's also a recent experiment by the group of Bromberg at Hebrew University, where they consider the backscattering cone for pairs of entangled photons. Okay, so here they are not measuring the lights backscattered, but they are measuring the coincidence between the pair of photons, okay, and they show actually the coincidence also follow the same time of behavior with the peak exactly in the back scattered direction. I'll give you some reference if you are interested to look at that. Question, don't forget to tell me to stop. I just finished with that. Yes, just a small question. Okay, we have more intensity in the backscatter direction. Okay, so but there must be conservation of energy. So where is this energy taken from? Okay, so people they ask this question and they found actually with a very accurate measurement that you have actually tails here that go below the cosine function. Okay. Actually, the energy is taken at the edge of the cone to build up the cone. So there is indeed a conservation of energy. So this is a paper that reviews this topic. If you need to, I'm sure you don't want to look at that, but if you need to for some reason, you have some good reference here. So maybe we make a break now, and then we switch to Anderson localization.
Yeah, little bit. Little bit.
But this will be more like qualitative.
它更新是啥时候更新？15号。
15号。
快了。
Okay, so let's start with the Anderson localization of waves in general. Actually, the story started with localization of electrons, and that was the seminal work of Anderson, Phil Anderson, 1958. Okay. So originally the concept of localization was proposed to explain the metal insulator transition. Okay, so you have a wire, okay, where you have a current flowing into this wire because you have always defects inside the structure of the metal. You have scattering also of the wave function of the electrons. Okay, so the prediction actually of Anderson, I will say a few words about that. So he has done research on amorphous materials, like amorphous silicon, for instance. And what he demonstrated, so this is a prediction, this is a theoretical prediction actually. He demonstrated that an electron can be trapped in a small region of space. And that's what we call Anderson localization. The fact that the extension of the wave function is limited within a finite region of space. So that's the main idea. And what he showed actually is that the diffusion constant, okay, which is supposed to be a constant, right? Actually, it depends on the size of the system, and as the size gets larger and larger, d of L, the diffusion constant, goes to 0. Okay, so you remember just before when I talked about the random walk, okay, the diffusion, the R square average was growing like d times, so the square was growing like d times t. Okay, so this d actually is not anymore a constant in this strongly scattering system. So that's what. So actually, Anderson got the Nobel Prize for this discovery. I mean, this prediction or this demonstration here. And actually, was not really believing in it. It's very. I mean, this. If you think about that, I mean, those people they think about ideas. Like in '58, you know, you have to wait like for like 30 years to start to see some demonstration of that. It's just amazing. So he said very few believed in at that time, and even fewer saw its importance. Among those who failed to fully understand it at first was certainly its author, so himself. It has yet to receive adequate mathematical treatment, and one has to resort to the infinity of numerical simulation. That's important, actually. There is no full theory to describe that. Okay, so the only way to demonstrate it is experimentally or using numerical simulation to show actually these effects. So he got the Nobel Prize. That's part of his Nobel lecture. So what is Anderson localization? So it's not that, okay, just for joking. It's not that, neither, okay. So that's the idea actually. So in this paper, so that's the similar paper of Anderson, absence of diffusion in certain random lattices. So what is the Anderson model? The Anderson model is the minimal quantum model, really the simplest model for studying the effect of disorder on particles, here on electrons. Okay. So let's consider a two-dimensional periodic potential. Okay, with each potential has a random random depth. Sorry. Okay, so the depth is changing randomly, but all this is on a square lattice. Okay, so you can describe that using this Hamiltonian, which is the Hamiltonian from the time bending model. Okay, and the random part is the on-site energy epsilon I here, which is taken randomly between minus W/2 plus W/2, and W gives you actually the degree of disorder of your system. Okay, so those are electrons in a kind of crystal structure with impurities. Okay, with the random variation of the depth of the potential. So the electron can tunnel through this potential. Okay. If it was a periodic system, so perfectly identical potential, you will see a region of the spectrum where you have complete transmission, and a region of the spectrum where you have a gap. Okay, if you are familiar with the crystals and propagation in crystals, there is if you introduce disorder inside the system, then what it demonstrates is that actually the particles here, although it is above actually the potential, the particle here can be trapped in a region, so not trapped by one potential, but by many of them. The wave function will extend to some degree, but will be blocked beyond a certain distance.
It will be stuck inside the material?
Yeah. It cannot escape actually from the system. Okay?
When there's like disorder and the L is larger, there's a lot of scattering, so there is an absence of diffusion.
Yeah, so the diffusion actually goes to zero. Yeah.
Go to zero.
Right. So that's the
How do you know how a large L needs to be?
size of the system.
The size of the system.
L is the size of the system. So that's a very good question. I mean, what should be the size of the system to make sure that we are localized?
Yes.
So that's what we'll discuss that. What is shown here simply is that for sufficiently strong disorder, okay, then the diffusion can be completely suppressed, producing spatially localized eigenstates and an insulating phase. Okay, so that means that if you have a conductor here for current, okay, but you have a lot of scattering, then the system is not conducting your current, but it's just blocking the current. The system is an insulator. Okay. So that's the main result of this work. So what is Anderson localization? Absence of diffusion. That means that the mid square, the R square average, saturates, goes to a limit. Okay. No diffusion at long times. I will show you different experiments. Very important, localization is not a perturbative effect. Okay, you cannot address this effect by a perturbation theory. Okay, cannot be captured by low-order perturbation theory. Arises from multiple coherent scattering and interference. You have to take into account all interferences inside the system. Okay, and this is fundamentally quantum. Okay, that means you have to consider waves with phase, interferences. Okay. Mobility age, actually there is a critical value of the disorder below which the modes are extended and above which they are localized. Okay, so critical energy where extended state become with the E localized. Okay? And finally, and very important, this effect depends on the dimension of the system. So the dimensionality plays a very strong role. I will show you that in 1D, all states are localized. Okay, so you take a wire, a one-dimensional wire. Okay, as soon as you have a little bit of disorder, okay, the system will be an insulator. It will not conduct current because all states are localized. Okay, so obviously you need to have enough length compared to localization length of the states, but it's always localized. In 3 dimensions, there is a transition, so there is a mobility H here at a critical disorder WC, okay, and the marginal dimension is 2D, okay, where all states are supposed to be localized also, but they are localized on quite large size. So maybe that reminds you something here. Do you remember anything about that? About the fact that the 2D is the marginal dimension compared to 3D and 1D? No? What we said about random walks? Do you remember? So what you say yes?
The probability for recurrence is 2. For the target states, for 2-dimensional is infinite. Is 0. The
The
probability.
probability of what? The probability of?
2-dimensional random walk.
Yes, that's the probability. We were talking about the probability of return.
Yeah.
What is the probability to return to the initial position? So in 1D, its probability is 1. In 3D, it's 0.
Yeah.
And 2D is marginal dimension.
Yeah.
So I'm going to show you that. I mean, that not me. I mean, that was shown actually by a very interesting approach, very original approach, I would say. So this is called the scaling, the one-parameter scaling theory of localization. So it's really with the hands, okay? So let's consider the conductance associated with some volume, okay? A box here of L by L by L, okay? So what we are going to show is that G is so with that, no, that's the hypothesis. Okay, we assume that G depends on the length. Okay, and we are going to do what is called a scaling theory. Scaling theory means that when I increase L, how my parameter changes with L. Okay, so that's what we call the scaling theory. Okay. So it's not a question of disorder, dependence on disorder, dependence on scattering strength, dependence on the size of the system. Okay? So you know that G, the conductance, is like the inverse of the resistance. Okay, so if you have two conductors in parallel, conductance are additive. If they are in series, conductance, the inverse of the conductance are additive. Okay, so that can be useful for next. So let's see. So the scaling theory of localization tells you that conductance G represents the ease with which electrons can propagate through the block. Okay. Actually, G is the renormalized dimensionless conductance, so forget about this detail. Okay, so the scaling function beta of G is defined as the rate of change of the log of G as a function of the log of L. Instead of looking G as a function of L, we are looking at log of G as a function of log of L. Okay, this is just for the following. So beta of G is d of log G over d of log L. Okay, beta of G tells whether the conductance increases or decreases when the system size is increased. Okay, that gives you actually the sign, the way it changes, the way the conductance changes depending on the system, on the size of the system. Okay, so the question is, when I increase the size of the system, do I increase the conductance or do I decrease the conductance? Okay. So the one parameter scaling hypothesis is that the function beta depends only on one parameter, which is L. Okay? So G, in other words, G only depends on L on the side of the system. So that's really the main, the central result here. I mean, the central hypothesis, okay? It's not the result itself. So let's see. I take this function and I try to find in the limit of very strong scattering or weak scattering in both extreme, okay? There is a way to calculate that, okay? So let's see. I am in a diffusive regime, okay? So I expect to have a strong conductance, a lot of light will go through the system, okay? So this just the expression of G is given by Ohm's law, okay? That tells you that G of L is L to the power D minus 2, where D is the dimension of the system. Okay? So if you have a one-dimensional system, it goes like 1 over L. Okay. So you just put in series. Actually, you build up the G in series. So it goes like 1 over L. If it's 2, it's a constant. If it's 3, it's going to be scaling like L. Okay. So if I replace here, I found that beta of G is just D minus 2. Okay, the dimension of the system minus 2. So I know one side of the story when I am diffusive, okay, for large value of G. Now, if I'm in the localized regime, okay, there is no more diffusion, so G should be extremely small. There is almost nothing crossing the system.
Can you remind what is G?
G is the conductance, okay?
Oh, okay.
So you measure how it is easy for electron to flow through the system, okay? If I am localized, they are like captured inside the system by the disorder, so G will be small, okay? If the regime is diffusive, so they will flow through the system and G is large, okay? So in the localized regime, what we expect is that the conductance will decrease exponentially, okay? Exponentially, so at the end of the system, at the edge of the system, you will have a very small conductance. So if you replace this function here, you find that beta of G is just minus L over Xi. Xi is the localization length here, okay? And this is exactly log of G, okay? So beta of G goes like the log of G, like the log of G here, okay? So we have the two extremes. In one extreme, you have a constant value. You see D minus 2 is just a constant, depending on the dimension of the system. And for the low value of G, we have a log function, okay? So we have these two extremes, okay? And we want to join them together, okay? So the hypothesis here is that there exists a continuous transition from one regime to the other. We can join the line if you want, okay? So that's what we get here. Okay, so this is a very famous picture here. Depending on the dimension, okay, so you have for G large, so this G, log of G here, so G large is here, G small is there, okay. So for large value, you have D minus 2, so for D equal 2, you have 0, D equal 3, you have 1, D equal 1, you have minus 1, okay. And here on this side, you have the log function, okay, so you have this log behavior here, okay, and you join the curves together with something which is more or less continuous and monotonic, right? And what you find actually is that for one dimension you are always below beta equals 0 here. For dimension 2 also you are below that value. But for 3 dimension, actually, you cross this line here, beta equals 0. Okay. So we said that beta tells you if the conductance is increasing with L or decreasing with L. Okay. So if it's positive, it means that it is increasing with L. If it's negative, it decreases with L. Okay. So what you see here is that 1D, 2D, you are always localized, okay? Beta is always negative. That means that if you increase the size of the system, the conductance decreases because the wave function is localized, is confined inside the system. And you see for v equal 3 here, there is a mobility h here. There is a value actually of g here in that case, okay, for which you can go either in that direction where you are localized, or can be in that direction where you are diffusive. Okay, so here beta increases with the size of the system. So this is diffusive regime, and this is localized regime. Okay, so this picture captures the difference between the dimension of the system. Okay, with a very simple argument. Okay, I mean you can argue, you can say that this is very too simple, and but that's what we have actually. We don't have much more than that in terms of theory. Okay, so the arrows along the curve represent how G changes what is system size. Okay, so when the size increases, G increases, and when size increases, G decreases. If beta is less than 0, then the arrow points towards smaller value of G. If beta is positive, the arrow points toward larger values of G. That's the interpretation of this diagram. So it tells you, to summarize, that in 2D and 1D, G reduces with increasing system size, and therefore the system is insulating, is localized. Okay. The localization length, which tells you how far you go inside the system. So there are some theory to predict the localization length. So you see that in one dimension, it's very simple. The localization length is equal to the mean free path. Okay, so very short. In 2 dimensions, it goes like the exponential of KL, K times the mean free path. Okay, so you see that if L has some value, the exponential can be much larger. I mean, see here the localization length can be much larger in 2D, and you understand why, because it's a marginal dimension. Okay, so there is like a divergence of this value. So that's where the length of the system plays a role. So you ask about the length of the system. Yeah, you ask about the length of the system, right? So you see that in 1D, localization is equal to the mean free path. Okay, so we can have a very small system. As soon as it is larger than L, the system is fully localized. In 2 dimensions, because it goes like an exponential, you need a much larger system to get localized, to see localization. Okay, so very important to compare the size of the system with the localization length, not the mean free path in that case. Very nice demonstration here. I didn't put the reference. Reference is missing here. Scaling theorem. So in 3D, there is a critical point, mobility H, okay, for which beta of G is equal to 0. Okay, so that describes actually a phase transition. It's a second order phase transition with a critical transition, and you see it here very well. This point here, you see that when the length of the system increases, so you go from black, red, orange here, you see that the conductance increases. Okay, so here we are in the diffusive regime. At that point, they cross, okay, and everything is reversed. Okay, so as the length increases, the conductance decreases. Okay, so because the energy is localized in the system, if I increase the length, I have less and less energy coming out of the system. Okay, is that clear? You can interrupt me and ask questions if you don't understand.
I have a lot of questions, but I will ask you later. This graph.
I want to make sure that you understand
This graph is zoom in to this graph.
So no, just to tell you that what happens here corresponds to this mobility H here. Okay, so on this side here, on this side, it corresponds to this side here. Okay, here, as you increase the length of the system, the conductance increases. Okay, so the arrow is in that direction. On this side, as you increase the length of the system, the conductance decreases. Okay? Just think about a wave function which is exponentially confined like that, okay? So if I take a small system, I will have some energy coming out, but if I take the system larger and larger, the tail of the exponential is smaller and smaller, and you get less conductance, less energy coming out, okay? So G is just how much energy flows out of the system, right? So here what they change is the disorder strength here, the W if you want. I think those are experimental, but I'm not sure. I don't see I don't put the reference. I have to find out where I took this from. But it looks like a measurement, I would say. So just to finish with that, so near the critical point, what did I say? G of L is sigma L. So what I want to say here? Ah yes, okay. So the question is, when you are near the critical point, if you write G of L as a function, a linear function of sigma of L, sorry, we said that G depends only on L, okay. So if you write it like a linear dependence like that, you can show that sigma, this parameter sigma here, has this form, okay, G minus GC, so GC is the G at the critical point over GC. So depending on which direction you take it, you have a vanishing conductance. Okay, so G goes to 0 near the critical value, so this term goes to 0 and G goes to GC. And from the left side, the localization length C diverges. Okay, I'm not sure this slide is very clear. This need more explanation. That's too fast here. Forget about that. So I want to show you back the movie that I showed you at the beginning of this course. I don't know why the screen is green here. This is green. If you want to see it here. I hope it will be okay on the screen. So this is a two-dimensional system, okay? It's a disorder system, so we expect to see localization, okay? But as you say, it depends on the length of the system. So it's for sure it is always localized, okay? But depending on the scattering strength of the system, the localization length can be much larger than the size of the system. So we won't see localization, we will see diffusion, okay? D of L is not yet equal to 0. So in that case, so that's the model, okay? We are going to simulate the Maxwell equation here. The background is index 1. The scatter, they have an index that can vary from small value to large values. The density, I mean the filling fraction is 40% here. The size is 120, so these really optical sizes, okay? So let's start with the average contrast of 0.5, okay? So you remember we inject energy in the center of the system, and then we observe the expansion of the beam inside the scattering system, okay? Sorry, I wanted to stop it at some point.
Can you explain what is the field that you see?
So you start with, you drop energy inside the system, okay, and then you let it propagate, okay. And this is propagating in the scattering medium that I showed you before, okay. what you see is that red means like high intensity, blue is low intensity, okay? And what you see actually, you have a wavefront here, okay? So this is the ballistic light actually that propagates at the speed of light inside the medium, okay? But you see that a lot of light is backscattered inside the system, okay? So it's not like when you when you throw a stone in the pond, you see these nice rings, okay? It's not only the rings, but there is a lot of light which is backscattered inside the system, okay? So on average, this system, the energy, if you take the average energy, it doesn't go at the speed of light, but it goes as the square root actually of
So all the colors are intensity of light?
yes, just intensity.
So it's not monotonic. It's not monotonic.
Yes, it's not.
כאילו שזה חוזר גם פנימה.
כאילו הצפיפות האור?
כאילו
כאילו מונוטוני?
הגל.
כן. תודה.
So it's a kind of speckle, by the way. It's like a speckle in time. And then you reach the edges of the system. Okay, you don't see any localization of the energy.
Wait, so the red spots are not the localization?
Ah, no. What you
You
see,
don't have any localization.
yeah, there is no
here.
localization of the
כן,
of
הוא לא תקוע בתוך...
The red is the amplitude, no?
yeah, the
Like,
colors. So when
it's
you have
a
a
higher
high,
amplitude, no?
yes, high intensity means that you have
Intensity.
constructive interference. Dark means that you have destructive interference. So this is a speckle image, okay? But the energy is everywhere in the system. Okay.
But now you will see localization.
Right. So we have. So I push a little far the contrast, okay, 3 and 1. And that doesn't exist in nature, I don't think so. But so here you see that the energy is constantly brought back into the center of the system, okay. So there is a slow spreading, okay, but it stopped that the movie stopped, okay.
Okay.
So, but it continues actually. If you wait for a very long time, you may have some tail that will reach
How long
the edges
time?
here. But
There is a time scale that we can see the energy go out
no,
of
no.
the...
I mean, what there will be some energy flowing out, but very small energy because this is really an exponential distribution inside. Yeah. Okay. So instead of the diffusive behavior, you have an exponential localized system here. Okay. But you clearly see now the speckle is very different. Okay, you really have very bright spots like that, and the rest is mostly dark. Okay, it's also reminiscent from the coherent backscattering cones. Okay, because you have energy coming back and building up constructively. So it's constructive in the backscattering and destructive in the forward scattering. Okay, so that's the connection with the first part of this course.
Why do we see in the picture more of the bright light instead of the red ones? Like most of the reds we don't see here.
Oh, I don't know. It's a problem of the color.
Like it's random or there is a reason behind it.
No, in principle, the red should be the highest intensity, right? I don't know. I'm sure there is a point which is red. We don't see it here,
Yes.
so it brings all the other colors down. But yeah, it's not. If I do it again, let's see.
Yes.
You see the red here.
Yeah.
No, this is simple actually.
Here you don't see red for a long,
Right,
long
right.
time. So what's
So
the
this
reason?
is simply because the movie is normalized to the maximum value at the beginning, okay. But then the energy spread a little bit, okay. So it goes down.
Like
On
exponent.
average, it goes down, okay.
Okay.
So you don't see any more red here. It's simply not for that. It's not normalized at each image. You see what I mean? It's normalized to the min and max of the movie, okay, which is at the beginning, and then as it propagates, the energy spreads, so it goes down, and you don't see the red.
If you do dynamic normalization, then you will see more red.
Say it again.
If you normalize per image.
Yeah, you could have normalized, yeah. But I wanted really to show the spreading of the. Okay, so I will tell you more about that, and that's okay. So the big question is, okay, I show you some theory, very little theory. We don't have much more than that. I show you some numerical simulation, okay? The challenge is to demonstrate that experimentally, okay? How can we demonstrate localization experimentally? I will show you several experiments that demonstrate the effect. I will show you that in 3D it's very challenging, okay? But to identify this phenomenon, you need some kind of signature, okay? You need to find signatures of localization that tells you, okay, in my experiment, I can certify that this is localization, this is not another effect, okay? So what do we have? So if we want to reach localization, one condition is the Joffe-Regel criterion, okay, which tells you what should be the constraint in the disorder. So if you look here, this KL, okay, scattering mean free path, so the distance after which you start to lose energy in the forward direction, okay, if you remember. This is not the transport mean free path, the scattering mean free path, which is smaller than the transport mean free path, times K. K is 2 pi over lambda, okay? So this formula tells you that lambda should be of the order of L, 2 pi L, okay?
Yeah.
So you imagine that the scattering length should be on the order of the wavelength, okay? So the wavelength, we are talking about hundreds of nanometer. So we need to have a scattering on this order, on this length scale, okay? So this is a very, very high constraint here in terms of scattering. You remember that this quantity, it was transport, not scattering, but this quantity was in the cone 1 over KL, okay? So if L is not strong enough, you have a very narrow cone, and as L becomes smaller, so larger scattering, then the cone becomes prominent. But you see, this is a very, very strong constraint. That means that you scattered on the scale of the wavelength, okay? This is very difficult to achieve, at least in optics. It would be easier to do that in acoustics, for instance, where the wavelength can be larger, or in microwaves, also in the microwave regime, okay? So that's one thing, one important criterion to think about when you want to design a system where you expect to see localization. Another important point here is, so this was actually a prediction by Sajef John. So what is the meaning here? Yes, so this is the mean free path here. Yes, okay, so I come back here. So this condition is based on the mean free path that should be small, okay? The question is how the mean free path varies with the scattering strength inside the system or the wavelength itself, okay? So if you see here so this is the mean free path here, okay? We want to make it as small as possible, okay? So you have two limits. One limit is where lambda is very small, okay? Very small lambda means you are in a regime where you have, so this is the regime actually of ray optics. Okay, lambda is small compared to the scatterers. So this is really like the regime of geometric optics, okay? So we know what is sigma, what is the mean free path, what is the scattering strength, and the mean free path is 1 over n sigma, okay? And the other limit, this is the Rayleigh, if you remember, the Rayleigh scattering, sigma for the Rayleigh scattering, the wavelength is much larger than the scatterers, okay? So you have these two limits here, and there is a minimum somewhere for the mean free path, okay? And you want this minimum of the mean free path to be equal or on the order of lambda, okay? So you need, you see this line actually tells you that you may have 2 points where you have a crossing between the value of the mean free path and the wavelength itself. Okay, so that's the region, that's a window, a frequency window or a wavelength window where we can expect to see localization, localized states. Okay. So in other words, it is shown differently here. So this is the frequency omega here. I guess, this is the density of states here, okay? So for low value of omega, you are in the Rayleigh scattering, okay, very small particles. On the other side, you are in the geometric optics regime where the scatterers are very big compared to the wavelength. Okay, so in between, they should be, I mean, you expect to have a window, a very narrow window, where you expect to see a localization, strong localization. Okay, so when you think in terms of waves and wavelength, okay, it's very hard to achieve the Joffe-Regel criterion, okay, and if it happens, it will be in a very narrow region of frequency. Okay. So that's the condition that we should have in mind. So I want to show you an interesting signature of localization. So this is related to the movie that I showed you. Actually, this is a result of my thesis. Okay, and so it's quite some time. Okay, and it shows the following. So it's a log scale here. Okay, we have a log scale. So those are simulations. Okay, and what I did at that time was to measure the extension of my wave in the two-dimensional system as a function of time. Okay, so what I see is that, and this is for different degree of disorder. Okay, as I'm increasing the disorder, I change the way that the wave spread inside the system. Okay, as a function of time here. So you see log scale. So if you have a linear, a straight line in log scale, it means the power law. Okay, so here for very small, very weak scattering, you have actually ballistic behavior. Ballistic behavior, you can find the slope is 1 actually. And then you reach the edge of the system, so actually it's blocked by the edge of the system. So if you increase the disorder, then you see that the ballistic regime then switch to a different slope. This slope is different from that slope. This is a diffusive regime. You expect a law in square root of time. Okay, so this is a slope of 1/2. So you have 1 here, 1/2 here. Okay, and as you increase more and more the scattering, then you see that the wave actually is blocked. The expansion of the wave is blocked in time. And then here you have a real proof. I mean, you can say you wait for a very, very long time. You see that you really saturate. I mean, you are blocked at some given size, which is much smaller than the size of the system. Okay, so it's not a size effect. This is really a quantum effect here. Okay.
Why there is more noise in
because because what happened actually is that if when the wave propagates, okay, it excites modes inside the system. Okay, there are many modes inside the system. When the modes are localized, actually the energy jumps from one mode to another. Okay, and if it is strongly localized, you have only a few modes that are actually activated by the wave. Okay, and what you see actually is the beating between the modes. Okay. So this was in something like 1993. Okay, and I will show you at the end that actually people they use this signature to demonstrate localization in 3 dimensions. So this was in 2 dimensions, but they use it as a criterion, as a signature of localization in 3 dimensions. It's in very recent works that I'm going to show you. Let me just finish with rapidly with the signature, and then we make a break.
Which year is it? Which year is it?
What?
Which year is it?
This 1993.
1990.
Your master was in 1993.
No, PhD thesis.
Oh, I see.
So this was my first paper actually. Okay. So you see, 30 years later, this was used actually to demonstrate localization. So other criteria, I go fast, okay, because it's a little bit. We discussed that already. Total transmission, so you remember the tube experiment, you measure, you integrate the total intensity at the output of your tube, okay? And what you see is that in the diffusive regime, the total intensity decreases as 1 over L, so if you increase the length of the tube, the transmission goes as 1 over L. If you are in the localized regime, because it's an exponential decay, so it will go like exponential minus L over C, where C is the localization length. So again, this is a scaling signature of localization, okay? But here, be careful, be very careful, because there is another effect that has exactly the same signature, which is something that decreases exponentially with the length of the system, is absorption. Absorption will have exactly the same behavior, okay? So this is a very bad signature because I think that I have localization, but this is not due to localization, but it can be due to absorption. Okay. So that's one of the main critiques here. The total conductance, so we mentioned that before in the scaling theory of localization. I skipped that. So yeah. The two-less criterion. So delta. What is delta here? What is my definition of delta? It's not here. Yes. So delta. So if you look at the spectrum in the localized regime, the spectrum. So this frequency here, this intensity. The spectrum in the localized regime and diffusive regime are very different. Okay, what you see in the localized regime, you see sharp peaks like that corresponding to localized mode, while here the change of intensity is smooth. Okay, so if you measure the width of the peak compared to the distance between the peaks here, you have a new parameter which is called the two-less criterion. Delta is delta nu, small delta nu over large delta nu. If delta is smaller than 1, that means that the separation is larger than the width. If delta is smaller than 1, then you are in the localized regime. If not, if delta nu is larger than the separation between mode, delta will be larger than 1. So that's another way. And the best way actually to characterize localization is to be able to excite the mode of the system. Okay, so if you can look at the mode, the eigenmode of your system, so you have an example here. So this mode actually is exponentially decreasing, exponentially localized. And so it's a scattering medium, okay? And you have a mode which is peaked inside the system, which is confined inside the system. How do we demonstrate that? So again, this is something that I did in the past. You have your scattering medium, always the same, okay? You excite here and you measure there, okay? So if you measure here, we find a signal that decreases with time. Okay, this is time here, this is intensity, so it oscillates and decreases. Okay, and then you can analyze by Fourier transform the time signal to look at the spectrum. Okay. So what I did here is to look at the spectrum. Sorry, I look at the spectrum here. For different time windows, I take the Fourier transform of this window, then that window, then a later window. Okay, so you think that there is nothing here, but there is a lot of information actually here, there. So that's what I do, and I take the Fourier spectrum, and you see that when you go longer in time, so this early time, medium time, and later times. Okay, you see that the spectrum decreases because the intensity decreases. But you see that there are peaks that survive in time, so they live for a very long time, okay? And those correspond to localized states. You can excite the system at one of these frequency, and what you find is this type of modes. So if you excite the system at that peak, A, B, C, D, okay, you get actually different modes of the system. Those are the eigenmodes of the system. You can decompose the field on this basis. You get actually a basis of mode that describes completely the scattering medium. So that's obviously, if you can show localized states, localized mode, then that's a nice proof for localization. Okay, and just to summarize here, I put a list of so this panel is localization. I should have written it here, and this panel is diffusion. Okay, so in the diffusion regime, D is constant. In the localized regime, D goes to 0 with the size of the system. Transmission is exponentially decreasing for localization. It goes like 1 over L. Okay. Eigenmodes are exponentially localized. In the diffusive regime, they are extended. Return probability, remember, this is related to the random walk. Probability to return is non-zero, is actually goes to 1 here. It goes to 0 in the diffusive regime. Okay. There are other parameters. I don't want to discuss those ones. So that's it. That's it for this part. So let's make a break, and then I will show you some realization of localization, some experiments in 1D, 2D, and 3D, and then we'll be done with this.
Thank you.
So we meet in 10 minutes, 15 minutes?
15.
15?
15 is okay. Can you come back to the what to the yeah
That? Or you want to?
yeah that.
Can you call the people? Okay. Okay, so let me finish with some examples. Localization in 1D. You can imagine that 1D will be the easiest way to observe localization. There is an experiment that you can do by yourself. So that's really one of the first experiments, 1986. Okay, I describe it rapidly. So you have a wire here with masses attached to it. Okay, and actually what is done is that you scan a magnet. Okay, along so the wire is close actually to a circuit. Okay, so you have some current going through the circuit, and by scanning the magnet, actually you measure the, how do you call that, the FEM, the voltage that is generated by the flux. So this string is vibrating. Okay.
The electromotive force.
So yeah, I was looking for the electromotive force. Okay. So by actually cutting the flux, the magnetic flux, you can measure the amplitude of the vibration. Okay. So it's very simple and a nice way to do that. And you see here they compare a periodic system and a disorder. So you scan. Oh, so this is frequency. Okay, for different. So this is a spectrum. Disordered system, you see, you remember the two-less criterion? The modes are relatively well separated, while in the periodic or diffuse regime, they really overlap with each other. Okay, and you can actually identify these peaks, and you can scan and measure the profile of those modes. So if you are in the periodic regime, you find the Bloch modes, so they are extended modes. And when you are in the disordered system, so you put the masses that are distributed randomly along the wire. You see very nice modes which are spatially localized. That's a very simple way. We did this experiment here in the microwave regime, where we have a waveguide, okay, filled with dielectric scatterers. Okay, so it's a 1D system because it goes along this 1D waveguide here, and we scan an antenna along the system to measure the field inside. So this is the microwave regime. Microwave, typically we are in the centimeter size wavelength. Okay, so quite big. The scatterer, they are about half a centimeter or quarter of centimeter. Okay, so if they are in a periodic position, periodic system, so what you find is the following. So I explained to you how to read this picture. So you have frequency here, you have position along the waveguide, so you have this long waveguide, okay, and you measure along the waveguide the spectrum, okay, so you see the amplitude of your spectrum, and you see a beautiful gap actually for this very large range of frequency. There is no no propagation in the gap, so it's a periodic system, so you expect to have a gap. Now if the position of the scatterer is random, that's what you observe. Okay, so again, different frequencies here. For some particular frequency, you can see a mode which is spatially localized in space. Okay, so you see the spatial localization of the mode. Okay, what you see here actually is the evanescent wave that goes inside the waveguide, which is actually doesn't go very deep. Okay, this is the evanescent wave. But for some particular frequency, you have actually a mode which is at given frequency and spatially localized. Okay, and here you have many, overlapping modes. So I guess this regime is more like in the diffusive regime. That's for one configuration of the disordered system. You can change the configuration and you get a new picture with other modes. You see those modes here, which are spatially localized. This one is close to, so the input, I should say the input is from this side, and this is the other side of the waveguide. Okay, so you come from here. So modes that are close to the input, you can excite them quite easily. The modes that are deeper inside the system are more difficult to excite. And that's a funny configuration here, where you actually can excite more deeper inside the system by a kind of tunnel effect. Okay, you can excite one mode that will excite another mode and another mode inside the system, which are localized and close to each other in frequency. So I want to show you in the time domain. Okay, if I launch a pulse in my system around those frequencies, okay. So that's where actually that's the case of the evanescent wave. So that's where I don't have any mode. So what you see is that the pulse comes in the system. Okay, so it comes like that, and it cannot penetrate the system. The system is so scattering that most of the energy is reflected back from the system, except when you are at one frequency of an eigenmode of the system. So this is the case here when you have one localized mode like that. So if I excite the system again with a pulse, so the energy comes and start to penetrate inside the system, excite the modes. Okay, so it goes in that direction. Okay, and the mode is excited, and the energy is slowly released because there is some very small overlap. So part of the energy is just flowing out of the system. And when you have like a succession of modes like that, so you have a funny dynamics of a pulse. You go from one peak, then to the second one, then to the third one, and you cross the system. Okay. So just to show you some funny observation here. There is a lot of physics behind that, by the way. That's another realization of localization that was observed for a Bose-Einstein condensate. So again, this localization of matter wave. So this matter wave within a speckle pattern. So the speckle pattern is the disordered system, the disordered potential, an optical potential, and the wave is matter. Okay. So here you see, this is very interesting actually. You see that the spreading. So they just drop at the condensate in the center of the system, okay? And what they see is that when you are far from localization, the pulse of atoms is expanded inside the system. You see the expansion inside the system. And when you are in the localized regime, you see that it's not expanding anymore. It remains confined inside the system. So this is very close to what I show you in my thesis. Okay, so the fact that with time you see that expansion is blocked actually by the disorder. And another example here. So this is actually a waveguide. So this is called a membrane. So you see actually it's a standing membrane of semiconductor. Okay, so this is very small actually. We are talking about less than 100 of nanometer thick. Okay, so there is a periodic structure on both sides. So this is called photonic crystal. propagation is forbidden here, forbidden there, so it can be only along this path here. Okay, so it's like a waveguide, a one-dimensional waveguide. Okay, but because such fabrication is never perfect, okay, so you always have some degree of disorder inside this structure. Okay, and that somehow traps the energy inside the system. There is localization, and the way to demonstrate that is by introducing inside the system. They introduce quantum dots that will emit light when there is energy. So for different wavelength here, and for different position, like the one I showed you before, you can see peaks corresponding to localized states inside the system. I don't go too much into the details, but just to show you that localization can be easily achieved in 1D. Okay, so that's another way to look in 1D system. How can I describe that? So you have actually, if you look, it's a waveguide with multiple channels. Okay, so it's a multiple waveguide actually. So it's like that. Okay, so different channels can be either periodic or randomly positioned, and they couple to each other. Okay, the light that goes in one channel can couple to the next one. Okay, so that's what you see. Actually, you see the extension here. So here there is no disorder. So there is ballistic propagation in that direction. Okay, so actually the length here is like time. So you see a spreading of the beam. In the diffusive regime, you see a spreading that goes like square root of time. You don't see it here, but it's here. And in the localized regime, then you have a confined behavior all the way through the system. Okay, so this is in 1D. So there are many demonstrations. I mean, several demonstrations in 1D. Let's go to a two-dimensional system. So this is an experiment that we performed in Nice, in France. So it's a microwave experiment. Okay, so you recognize here the network analyzer. So it's a kind of microwave cavity, which you see here. Okay, and this cavity, inside the cavity, you have dielectric cylinders. Okay, all these cylinders, they have very high index of refraction for microwave. So the wave is excited. You can see some holes here where we can put an antenna to excite the system. And we measure, I'm not explaining here how we measure the intensity profile inside the cavity, but I show you the result. So I just keep the method here. Okay, so you see where you see the position of the scatter you cannot measure, okay, but you can see the distribution of the intensity is localized inside the system. Okay, so we have strong localization now, this time in 2 dimensions. So this is an experiment demonstration of a localized state, localized mode inside the cavity. So this from one frequency, you have another one at that frequency here. Okay, so you see how the wave is trapped within the system because of disorder. You see that the trapping is not just a trivial trapping between the scatter. I mean, the wave is extended on a large area, okay, beyond these small cavities between scatterers, okay, and even though it's a localized state, here is another one here, more localized, more confined, and this one even more confined, okay, localization. Another approach that has been strongly investigated is called transverse localization. Okay, so the idea is to have a system which is invariant in the z direction. Okay, but you have some scattering here, so it can be like fibers. You can put fibers with the random position. Okay, and they are coupled with each other. So that was shown in different works. This work by Moti Segev at the Technion, where they show localization. Here they show localization along the system. Okay, you can see actually the structure, the section actually of the structure. Okay. So this is for optics. I can show you some results for acoustics that we have done here in the lab. So this is actually a plate. So it's a vibrating plate, okay? But we fixed randomly the plate at different positions. So it's clamped at different positions with these screws here. So it's a very funny system, okay? So when you clamp the plate, it cannot vibrate. So the vibration is between those scatters, between those screws, okay? So that's one experiment. There is another one where we have a plate here, also a vibrating plate. Actually, it's a silicon wafer with holes, okay? And what we observe in this plate, actually we can measure localized states, localized modes. So this experiment, this is simulation. For a particular frequency, you see localized states on a linear scale or log scale. So you see that it is extended everywhere, but the maximum of energy is really localized there. That's one mode. That's another mode here. Very nice. I'm skipping this experiment. It's too long to explain. Okay, so let's go to 3 dimension. Okay, so that's where we have the big challenge. So you remember localization in 3D is not guaranteed. Okay, if you don't have enough disorder, you'll be above the critical value, the mobility age. Okay, and you'll be diffusive. So you need a very strong scattering to observe localization. So there is this experiment that we have been working on with the Queen's College in New York, and we are doing experiment 2 here, where we have this tube. I already described this experiment, and there is a frequency window. You remember there is a frequency window where actually here the fluctuation becomes huge fluctuation of the total transmission, and this frequency region is a localized region. We can show that we have localization in this region. You can calculate the conductance, you can calculate the total transmission. I don't go into much details here, but that's something you can come visit the lab. CD will demonstrate to you localization in this system. So that's more probably so just the criticism here in this experiment. This is a tube, so a very long. One dimension is long, and the other 2 dimensions are small. Okay, so it's called quasi one-dimensional system. It's not a pure 3-dimensional system. Okay, so you force by having a tube like that, you force the confinement in the transverse direction. So people say this is not true. 3-dimensional system, people argue on that. So there is one experiment which really demonstrates 3-dimensional localization, but this is in 3 dimensions. So actually they have this sphere, these metallic spheres, okay, and they just hit the system, so they sinter actually the beads, they get glued together, okay. So you have actually energy that can propagate from one ball to the next by small contacts, okay. And what they show, so if you remember the distribution of intensity, so this is a function of time, but why is that as function of time? Yeah, no. So this is not the distribution. This is just the diffusion as function of time. So what you see that. So wave is launched inside the system. So when it's in the diffusive regime, you can fit the data by the diffusion theory. So you have an exponential decay with time. When you are in the localized regime, then you have a stretch exponential here. Okay. So you are beyond the localized regime, the diffusive regime. You get closer to the localized regime with the signature here. And yes, so this is shown here in the statistical analysis of the data. They look at the speckle and they look at the statistic, and they find a departure from the diffusive regime for the exponential decay, which gets larger and larger. And Yeah, actually that's what they have. I mean, they don't demonstrate localization. They demonstrate a very strong mesoscopic effect. The question is, do we have localization or not? What about light? And I will finish with that. Localization of light. So that's a huge challenge, and this actually to date it's not demonstrated. Localization in 3 dimensions is not. There is no clear proof of it. There have been many samples that have been explored. One of the main problems is that when you are in this regime of localization, the light spends a lot of time in the medium. Okay, so if you have a little bit of absorption, the absorption can start to dominate the process. Okay, because the light stays longer in the system, so it is more and more absorbed over time. Okay, and the exponential decay that you expect for localization can be simply due to absorption inside the system. So here, for instance, that's an experiment that was done by the group of Maret. So this one has been done recently, to 2013. So this is exactly the experiment, the numerical experiment that I showed you back in time to my thesis, okay, where you look at different times, you look at the expansion of the beam inside a scattering medium, so it's a dielectric scattering medium, and you show actually that at some point the expansion of the beam remains mostly concentrated at the center of the system. Okay, so they studied the dynamics of the pulse, and they looked at the transverse expansion of the beam, and they showed that there is a regime where diffusion seems to be stopped actually in the system. But there have been actually after that there have been other papers which show that the same effect can be observed if you introduce inelastic scattering or incoherent processes. Okay, especially what they found is that in this system they launch a pulse, quite high energy pulse to propagate through the system, and actually you have very weak non-linear effect in the system. Okay, but because you stay very long inside the system, you accumulate the effect. The non-linear effects are cumulative. Okay, and actually they dominate the observation. So there have been like a lot of back and forth between these papers and some controversy on these papers, and at the end, actually, the author they really recognized that it could be something else than localization. So there is no proof here. And the last really papers that came out in the field. I didn't put the reference here, by the way. This is not experiment actually. This is a simulation. But I wanted to show you actually the same idea. They excite a 3-dimensional random system, and they observe as a function of time here the expansion of the beam inside the system, and they compare the diffusive regime here where you have an expansion over all the system, and the localized regime where actually the energy remains localized inside the system. Okay, so if you look at the output as a function of time, so if that reminds you my old picture of the thesis, okay, you have, so it's not on a log-log scale here, it's on a linear scale, so you have a diffusive regime, diffusion here, wave goes like square root of time, okay, but in the localized regime, so they just increase the number of scatterers here, they show actually a saturation, so the wave cannot expand further inside the system. So to do that, they use actually metallic scatterers, okay, aluminum spheres here. This numerical simulation, so it's very easy in numerical simulation to suppress absorption or nonlinear effect, okay. Now the challenge is to do that experimentally, okay. So actually there is no demonstration of localization in 3D for light. There is one for acoustics, but nothing for light. So these numerical simulation, not experiments. So with that, I finished, and it's still an open problem. So if you are interested in the field and you want to work on the topic, so back to the 50s, I mean, where it was really predicted by Anderson. We are still waiting for the ultimate demonstration in 3 dimensions. Okay. Thank you for your
Thank you,
attention.
Patrick.
Thank you.
so much.
If you want to discuss any part of this topic, I was a little bit fast because I don't want to go too much into details. But if you are interested in one particular experiment, I can spend more time on it. Okay, thanks. So next time I will give you some application. I will try to go over several applications of light propagation in disorder system, not necessarily localization. And then it will be your turn to tell us about this physics in the paper that you are preparing.
Yes.
Okay?
There was a slide in the last time.
זה בדיוק סיגריה.
8 דקות?
לא,
9
不是他这个脑回路是什么玩意儿？人家都用回路。